force density using leverage out mechanical systems. And so we discussed the possibility of measurements of the Casimir effect in a new regime, and then today we're going to continue and discuss what one could do in the area of deviations from Newtonian gravity in these complicated mechanical systems. And then at the end, I'll touch on a possible new application which involves using these levitated sensors to detectors for gravitational waves at really high frequencies. Okay, so let me just skip through this Casimir material since we went over it last time. So basically, just to quickly recap, the idea is you have an optical cavity here with a metallic mirror on the side. You trapped the nanosphere in an antinode of the standing wave in this cavity that's occurring close to the surface of this mirror. And now the idea is to measure the Casimir force between this sphere and this metallic plate. And you can really do this over a wide variety of distances. So particularly you can measure it at a short distance limit where the sphere is close to the plate, and also extend this out all the way to the limit where the size of the sphere is small compared to the separation from the wall. And this region in between here has really never been studied experimentally before. So in the short distance limit, you expect the scaling to go like the separation from the surface cubed, and the force in the long distance limit goes like the separation distance to the fifth power. And so the idea for the measurement is quite similar to what was done with the measuring the center mass oscillations of the low mass condensate at Gila. So that is, you have the gradient of the Casimir force produces a fractional shift in the resonant frequency of the mechanical oscillator. So it acts like an extra spring constant, if you like. Right? So you can look at the ratio of this force derivative to that spring constant from that this fractional change of frequency, and that's what's plotted here on the vertical axis. And now this is as a function of separation. So you can ask, well, if your thermal mode is limited with your sensitivity, what is the best sensitivity you have to some kind of a fractional frequency shift like this? Calculate that, and it goes like square root of kT divided by the frequency times the spring constant times the Q factor times the RMS oscillation amplitude. So in this case, we're specifically driving the sphere into some oscillation and looking at the fractional frequency that's measurable. And so for an oscillation frequency of 5 nanometers, this is a fractional shift of 10 to the minus 8, which is quite, which allows you to really extend the distance. Time when I say this now, you really extend the distance between the plate and the sphere over several microns down to hundreds of nanometers. So in addition to the Casimir force, we'd like to also think about measuring tests for Newtonian gravity. In particular, what we're really looking for there is physics beyond the standard model of particle physics. And so, although the LHC has yet to discover anything on Higgs, there's still, I think, really good theoretical motivation that suggests that there's going to be something in addition to just the standard model. And so that is, there's a really big energy disparity between the energy scale of electrical weak interactions. This is the TeV energy scale, and then the Planck energy scale is the energy scale of quantum gravity. And this vast area here with this 16 orders of magnitude has really no known physics in it, so they call this the desert. There's an appropriate specific setting. And so the problem that's caused is not, this isn't completely inconsistent, but it causes a very unaesthetic problem that's referred to as the gauge hierarchy problem. So if you look at the standard model Lagrangian, so the Higgs has some mass, some bare mass square as a parameter that this will be Lagrangian. So if you look at quantum corrections, so here's an example of a Feynman diagram, the Higgs mass is going to be corrected from the radiating corrections in quantum field theory, and this correction is going to be cut off at the highest energy scale in the theory, which is its Planck mass. So what that means is that in the standard model, I have to take these two terms, this bare mass squared and this Planck mass squared, and I have to subtract those two numbers. And they need to cancel at the 32nd decimal point to have what's left over be a physical value for the big mass. So this is a really finely tuned situation. It's kind of like standing up a pen in such a way that it stays perfectly straight for some ridiculously long period. I mean, it's very, very unnatural, right? So there have been a lot of theories that suggest solutions to this. So the most popular, which is one of the ones that is being searched for at the LHC, is the idea of supersymmetry. And the more recent idea is that there could be large extra spatial dimensions around. And in this case, the fundamental scale, this fundamental scale of quantum gravity could actually be at a much lower scale, which would eliminate this fine-tuning power. But the point here is that either one of these possibilities, whether it's just supersymmetry or this other idea of large dimensions, gives you some possibilities for new physics that will show up in gravitational tabletop measurement at the millimeter level scale. And so in the first case, if I just have supersymmetry, so for example, supersymmetry can be embedded in string theory, which is it's one of the popular ways of unifying gravity with the other standard model forces. And so in these string theories, there are a lot of extra dimensions, so 10 or 11 dimensions, depending on what theory you're looking at. And these dimensions are typically really small in size, and there are particles that describe the shape and size of these extra dimensions. And so these particles, if they exist, they have to have some mass, otherwise we would have seen them in an experiment. So the idea is that they could get a mass from breaking of supersymmetry, and depending on how that supersymmetry is broken, the natural scale for this mass makes their Compton wavelength right at the millimeter scale, which is kind of the scale that you expect to start to see deviations in these experiments. And so just to really schematically, roughly sketch out how this works. So the couplings in the standard model, for example, Cow couplings that give you the masses of quarks and leptons and stuff around, and the gauge couplings can depend on these moduli fields from string theory. And so if you bring two nucleons together, they can exchange, for example, a gluon modulus. So the gluon is the mediator of the strong force. So they can exchange this gluon modulus, and in doing so, they can create a potential that looks like a correction here to the Newtonian potential between these objects, where you have this strength here, alpha, which is just some number that describes how strong the interaction is relative to gravity. And then you have some length scale here, which is the constant wavelength of the particle, which describes what range that interaction occurs in. And the natural scales here turn out to be right at the millimeter scale, and the strengths here are naturally for gravitational strength. In the other example I mentioned, where you have these large extra dimensions in space, so the idea is that our world is some four-dimensional slice of some larger dimensional space, and light and the forces, the standard model forces we know about, only propagate in our four-dimensional world, so our three dimensions of time, three dimensional space and one time. But gravity could propagate in all of the other extra dimensions, and in doing that, gravity, the effective strength of gravity gets diluted by the volume of the extra space. So gravity looks very weak to us in relation to the other forces. It's much, much strong, much, much weaker than the electromagnetic force and the strong nuclear forces. And maybe the reason it looks weak is because it just gets diluted because it propagates out of the other dimensions. And if you arrange the situation, then you could explain the observed value of the Planck mass as some fundamental scale that really might be closer to the other scales of physics we know about, say the TE scale, times this volume factor of the extra space. So in this case, we wouldn't have to fine-tune the standard model to get the energy scale such that it cancels into the 32nd decimal point number for the Higgs. Okay, so the consequence of this is that if I bring two masses closer together than the size scale of these extra dimensions, then the Newtonian force, which scales like 1 over the distance squared between the masses, now changes to 1 over the distance, so 2 plus n to the power. And so what you expect to see is that below that distance now is force law requires some new power dependence. And so it's also possible to have these extra dimensions. I could not only have gravity that extends into it, but I could have other kinds of fields, vector fields, or scalar fields, and these kind of fields can also provide some visible consequences at the millimeter scale. And in some cases, the force with a vector particle, imagine that baryons, there's some gauge field that couples the baryons that propagates in the bulk. The natural scale for this strength relative to gravity goes like the fundamental scale of the Newtonian mass squared. So now we're talking about forces here that are 1 million or 100 million times gravity. So there's kind of a range of different possibilities for these theoretical predictions of what one might discover when you put out the Light Moduli. Also, you can have scalar particles, and in this case, it would be attractive, or in the case of vector particles, you get repulsive kind of interactions. But the point is that all of these things come together to give you this sort of Bucala type. You can always use this Bucala type experimentation to describe what's going on here at short distance, and we expect that this lambda here is going to be below the millimeter scale. Okay, so I talked about in the first lecture our experiment that was done at Stanford. I just wanted to, before I describe what we could do with these levitated optical systems, just wanted to say a couple of slides briefly on some of the other experiments that are operating in this field. So at Stanford also there's a next generation experiment where we've replaced this oscillating structure here back and forth underneath the cantilever device by a rotating helium gas barrier. So this is a cryogenic helium gas barrier where asymmetric flow of helium causes this thing to spin. You have a spinning pattern of masses underneath the device. So the sensitivity of this experiment relative to the other one should be expected to be improved by about a factor of 10 or 100. So there's still some still ongoing new results that comes, but probably in the next few years that's likely to happen. At larger length scales, there was an experiment, actually several experiments at the University of Washington, where they use a torsion pendulum that has a set of holes cut into it, and they take another attractor mass here with a matching pattern of holes, and they spin it, and then they look at the torque exerted on this plate. And from that, they can make measurements at kind of 100 micron or 50 micron sort of length scales. At the University of Colorado, and now this experiment is now moved to Indiana University, Bloomington. They have a kilohertz frequency tungsten torsional oscillator here, which looks at the gravitational force between a test mass and this test mass and the source mass that's from nearby and detected electrically. And so what can we do with an optical mechanical system? So again, here's a picture of an optical cavity. So now imagine I have this nanosphere, it's 300 nanometers of diameter, that's trapped in the first antinode of the traffic field where I get a reflection off of a metallic mirror. And there's a second light field in this cavity here that we're going to use to cool the motion of the sphere, and that wavelength is chosen such that at the first antinode surface, when I'm at a position of maximum intensity of the trapping light, I'm also at a position of maximum intensity gradient of cooling light to facilitate the maximum cooling possible. And so I'll measure the position of this oscillator by looking at the phase of the reflected cooling light coming out of the cavity. Okay, so behind this mirror now, I can think about the position of the mass. So here we have the idea is to have a patterned array of masses again with different density materials. So you have area with dense gold material and then less dense silicon material. And this has now a width of 2 microns across and is mounted on a Maven's type actuator, which oscillates the device up and down in this direction with an amplitude of a couple microns. And so the idea is that as this device mechanically oscillates up and down, the density modulation here is going to modulate the gravitational force on the sphere. It's going to excite it into some oscillation of the axis in the direction of the cavity. And so We also need to be careful because the hypersensitive is also very sensitive to, for example, a Casimir force. If one does the calculation, you find that the Casimir force is actually about 10 to the 5 times stronger than the gravitational effects we're looking for. And so we really need to screen out that Casimir force in order to make a measurement of gravitational effect. And so here, the idea is to use a conducting mirror. That's the primary motivation for using that conducting boundary condition. This turns out to limit the cavity finesse, but it turns out that the cavity finesse is significantly limited. So the mass itself also, in order to take additional precaution to avoid having a periodic kind of coupling from the Casimir effect, we'll have a thin layer of silicon and an insulator and then a gold uniform layer on top, so that there's a uniform equipotential surface that's presented to the sphere, as opposed to having this corrugated materials where you principally have different Casimir forces just because of different thicknesses of materials. And then, of course, also we have the capability of changing the equilibrium position about which this driving mass oscillates. And so the idea here is that suppose you do your experiment and you see some sort of interaction in the sphere, and you want to know, is this gravitational interaction that's driving it? Also, you'll distinguish that from, say, just a vibrational background. Say I'm just shaking my experiment, and I'm shaking the sphere, and that's what's going on, and there's no gravitational interaction at all, right? So the idea here is that, so this device is moving back and forth, and I can arrange it such that if the center position or the equilibrium position of this oscillation is such that the sphere is right between a dense section and a less dense section, then all of the odd harmonics of the force, in particular the third harmonic where we're measuring, all of the odd harmonics of the force get maximized, and all the even harmonics disappear. And when the equilibrium position of that oscillation is such that the sphere is sitting above one of the dense materials or over one of the less dense materials, then all of the even harmonics are maximized and all the odd harmonics disappear. So if I simply translate the measurement device and repeat the measurement many times, what I'll see is that there should be a modulation. If there's a real force there, that will modulate according to this periodic pattern in the material. This is a nice way that we can separate a real effect from other kinds of backgrounds, which might just be exciting device. And so here's a lot of roughly what we estimate we hope to be able to do with the system. So that this is, again, this Newtonian potential, this correction term from all this new physics that I briefly mentioned. So the vertical axis here, again, is the strength of these new interactions relative to gravity. So gravitational strength down at the bottom, and then up to 10 to the 9, 10 to the 12, 15 times gravity. The horizontal axis, length scale, the interaction turns on. The yellow area here is what's previously excluded by experiment. And this shaded areas over here are some of the theoretical conditions that I mentioned. And so with these two curves here are what one could expect to do with spheres of different sizes. So for a 150 nanometer radius sphere and a 1.5 micron radius sphere. And so you see that sort of the micron sort of length scale is about a factor of 10 to the 6 or so possible improvement over previous length. So this is kind of potentially a pretty big advancement. So there really are some of these other strange physics here, type things going on, and maybe we have a chance of seeing. So, any questions? Okay, so then let me go ahead and to go on to the final part of the lecture, and that's I'd like to discuss the possibility of using these kind of systems for gravitational wave detection. So here's an example of one of the gravitational wave interferometric observatories. This is part of LIGO that's in Livingston, Louisiana. And so there's a lot of experimental evidence, I would say, for general relativity, right? We know about gravitational lensing, we know about perception of perihelion and mercury. We've indirectly seen evidence for gravitational waves, but direct observation of gravitational waves, I guess, depending on who you ask, is kind of look at as one of the last pieces of general relativity to really, confirm the theory is correct. And so there are some, several types of sources for these waves. For example, we have astrophysical objects that are inspiraling. We have other kinds of stochastic background type sources like inflation or cosmological phase transitions or things of that nature. And so the most convincing indirect evidence that there are gravitational waves is from the Pulse and Taylor binary. So Pulse and Taylor were awarded the Nobel Prize in 1983 for this discovery. So basically, they looked at a binary system of neutron stars. And so there was a rapidly spinning pulsar which emitted electromagnetic radiation at a really high frequency, say 17 hertz compared to some of these other frequencies, that orbited around another neutron star with a period of about 8 hours. And what they did was they looked at this orbital period over a period from 1975 to 1983, and they looked at how that period sped up. So the rotational period between those two stars sped up by about 14 seconds over that time period. And it followed this nice quadratic behavior that matched perfectly with the general relativity prediction that you'd expect from if that energy was being lost to radiation into gravitational waves. And so, like I said, this Nobel Prize winning work, but nobody has yet to actually detect the influence of the gravitational wave. All we know is that the energy lost by the system is consistent with the emission of gravitational waves. Okay, so you can think about gravitational waves as they propagate as basically stretching and squeezing the space between, as I said, two test masses. So two masses that are separated by some length L. The gravitational wave comes along, say, in the direction of the board. What it'll do is it'll stretch the space-time so that this length will vary, and there'll be some strain. So the physical distance between these two masses is going to change. There's some strain that we'll typically call h, which is just given by the fractional length change. And so a strong gravitational wave will give you a bigger h. And for gravitational waves, they propagate with tensor radiation. They propagate with two different types of polarizations, plus and cross, which basically you have two test masses along one axis, while those test masses are brought closer together. Test masses on the other axis, those axes get pushed further apart, and then the pattern oscillates. Contrast that with, say, what you expect from electromagnetic dipole radiation. There are two polarizations that we don't think about every day. So the sources for these kind of waves have to do with accelerating mass, essentially. So you can think about, just as a typical example, of neutron star binary. And so we all know for E&M, if you have a charge that accelerates, it's going to radiate electromagnetic radiation. In this case, if I have an accelerated mass, I'm going to get gravitational radiation. So now it's not dipole radiation, it's quadrupole radiation. So I need some kind of asymmetric pattern rotating in order to generate a quadrupole moment to get quadrupole. The canonical example is two rotating dumbbells, or a rotating dumbbell. So you have two neutron stars that are undergoing some kind of in-spiral motion, and eventually they'll come together and coalesce. But so the typical scale for what you can ask, what is the strain in space-time that you'd expect to see on Earth as a result of the gravitational wave produced by this astrophysical object, this spiral. Right? So the scale turns out to be roughly at the level of 10 to the minus 21, so this is a pretty small number. And the frequency scale, this varies depending on the source. It could be something like a couple hundred hertz. So there's a variety of sources that are present at much lower frequency, and also something higher frequencies. But this just sort of gives you the scale for what kind of strain you're really trying to detect. And so there's now a couple of different types of detectors that people are using around the world to look at these things. So the first type of detector is so-called resonant bar detector, or Weber bar detector, after this guy, Joe Weber. come by this thing basically rings like a belt. So the gravitational wave comes by and it stretches space-time, and this mass undergoes some ringing oscillation. And so the thought is, well, if I detect that ringing oscillation at the resonant frequency of this bar, if I have a high Q, I can get a big enhancement. Right? So I can see a big displacement of the ends of this bar if the gravitational wave that's passing happens to have a frequency that coincides with the frequency of that bar. And so in modern times, there are still detectors of this kind operating around the world. This is just an example of one of them. This is an experiment in Italy where they have almost 2.5 tons of aluminum and a 3-meter long bar that's sitting in a dilution fridge at 0.1 Kelvin with a Q factor of above 10 to the 6, resonant frequency of 900 hertz. And they measured the motion of those ends of this passive wave. The strain that they're sensitive to is right at the level where you expect to see these kind of signals, right? So 10 to the 21 in terms of the strain, delta L over L per root hertz. So there are also even more sensitive than these detectors are these interferometer detectors. There are several of these operating around the world. So the idea basically is you take a laser, you put it in a Michelson interferometer, and I have, at the ends of the Michelson interferometer, I have these fabric flow cavities. And what I look at here is, as gravitational wave propagates in this direction, perpendicular to the interferometer, space-time gets stretched. In particular, the physical distance between the test masses along this arm is compressed. The physical distance between the test masses along that arm expands for the polarization of the wave. And that causes a phase shift in the interferometer, right? So light propagates the arms of the interferometer, the mass position changes, and now the accumulated phase shift. This cavity, you get to detect. By detecting the displacement of the mirror using the phase of the light coming out of the interferometer, I can determine what is the strength of the gravitational wave. So you want to measure again h, the strain delta L over L, and so in these kind of experiments, they're measuring h roughly of order 10 to the minus 22, which the detector arm lengths here are a kilometer radius, so that means the position measurements have to be at the level of 10 to the minus 19 meters to get this kind of strain sensitivity. And so the limitations in this, there's a few kinds of noise that limit these detectors. So at the high frequency end, these detectors are shot noise limited, just the number of photons detected. So that's because high frequency, the cavity, technical frequencies above the cavity line width, has some difficulty in resolving displacements as we were discussing yesterday. At lower frequency, there's some thermal noise in the suspensions of these masses, and then also very low frequencies, there's ground motion and seismic motion that have to be dealt with. And so, I mentioned there are several, there are 2 LIGO detectors in the US, there's Reno, Italy, GO600 in Germany. And so I can look at the sensitivity curve for LIGO. So this, actually on the right here, is data from their 5th science run in LIGO, which was a few years ago now. And what's shown here is that this is the strain sensitivity in square root of hertz, and this is the 1 per square hertz right here. This is the frequency of the system. So above, say, a couple hundred hertz, the strain sensitivity is limited here by photon shot noise. So the cavity has some length, there's a finite amount of time light is stored in the cavity. Right? So the cavity has some line width. If you're doing a measurement at a high frequency, so that cavity pole frequency comes right around 100 hertz. If you're doing a measurement at really high frequency, then the cavity is no longer a good sensor position. Right? And so we're seeing this effect here where we're limited by this photon shot noise. At lower frequency, the thermal noise of the suspension takes place more. And then at even lower frequencies, tens of hertz range, now we're looking at seismic effects on so this was the noise budget, if you like, for this sensitivity. And LIGO actually is operating at its design sensitivity, which is pretty impressive for any instrument, particularly something this complicated and large. But so this dark red curve here roughly shows the same shape that we're seeing here in the data. We have shock noise here, suspension noise, and seismic noise. And yesterday we heard some great talks about radiation pressure noise. And if one looks at the shock noise here at low pressure, radiation pressure noise actually would tend to place, low frequency radiation pressure noise actually would set some limit in terms of the strain that one could detect. And in fact, in the next generation of advanced LIGO detectors, they're actually expecting to be limited over some frequency band by this radiation pressure effect that people were talking about measuring very recently in the last lectures. So what can levitated systems do for gravitation? Well, so I should mention, actually people have been thinking a little bit about this even many years before this mechanics community really started to take off. So Ken LeBrecq and Eric Black had an idea where they were looking at optically levitated masses back in 2004 as a way of eating the standard quantum limit position measurement. And so the idea I'm going to talk about today is not the same as this, but rather I want to consider kind of a membrane in the middle type approach where you have some resonant levitated sensor in the cavity, and I'm going to try to do resonant force detection to measure gravitational wave. And so now what we've done is basically, you think about it as we've replaced the problem of making a very precise position measurement at the ends of my cavity with a problem of making a very good force measurement of the force on this mechanical oscillator in the harmonic track. Okay, so our measurement is not going to be limited by the shock noise, our ability to measure the displacement between two objects. It's going to be limited by the thermal noise in the force measurement, the force that the gravitational wave imparts on our sensor. Okay, so here's what it might look like. So you have a cavity. Now imagine I have two standing waves in the cavity, and I've got one standing wave that's going to localize and trap the sensor at some particular antinode. And I've got another standing wave that I'm going to use to cool its motion and also read out its position. And so let's consider, for example, I could do this with a silica sphere. So if I take a silica sphere of 150 nanometers, like we're thinking about in our other experiment. Or I can also use a disk. So I mentioned last time the benefit of using a disk type geometry for having a reduced scatter. And so, for example, let's consider a disk with a thickness of half of a micron and a radius of 75 microns. So we think about a curve that at 1.5 microns, so that 500 nanometers is still sub-wavelength. And let's consider taking this thing and putting it in a very large optical pattern. So I don't mean large on the scale of LIGO, but I mean large on the scale of a very large group, so say 10 meters or 100 meters. And so the idea is we'll use one laser to trap the particle, and the second laser cools and measures the position. So gravitational wave comes along through the system, and it stretches space-time. So I can write that in terms of what it does to the metric, general relativity. And so the metric is going to be stretched by this factor h in the, say, x and z direction. The gravitational wave is propagating on the y direction, so along the cosine of t minus y. And so what happens is that the gravitational wave is going to change the physical distance between the end mirrors. So the end mirrors here are separated by some distance L sub m. Then, as time passes, the physical distance of the system is going to be modulated by this function here, which describes the passing of this gravitational wave. Okay, so also the physical distance between any test masses or gravitational wave should have the same amount, also the physical distance between my input here and the sensor is also going to get modulated by the same effect. Right? So I can get this physical distance. It's going to be this x. So s, the coordinate of my sensor, with the correction where it gets modulated by gravitational wave. masses. Okay, but now if I look at the effects of the gravitational wave moves the end mirror, right? And so what that winds up doing is, if I look at how the light propagates in the cavity, it displaces the physical position of the antinode of the trap with respect to the sensor's physical position. And so the antinode shift goes like 1/2 times length of the cavity times the strain. And then also the sphere, as we showed last time, changes its position by 1/2 times the sphere's coordinates. And so I can look at the difference of these quantities, right, and figure out that the sensor is going to get moved with respect to its trap position by an amount that goes like 1/2 times the strain times the difference of these two coordinates. So, and then there's a correction that I'm collecting that to order the strain squared, but the strain is already so small that we don't care about the strain squared. Right? So the idea here is that if I put the sphere close to the input mirror, I have a very big effect. And if I put the sphere near the end mirror, then actually this effect disappears. So to operate this experiment, I really want to have the sphere close to one of the sides of the cavity. Any questions? Okay. So then I can ask, okay, well, I've displaced the sphere from its equilibrium position. What does that do? Well, it produces a force on the sphere, right? So the force from the gravitational wave, it's going to look like the spring constant, it's going to look like m times the gravitational. No, sorry, I think I have this. Well, yeah. Okay. So the idea here is we're going to tune the intensity in the cavity, right, so that the gravitational wave frequency matches the mechanical resonance.